So the last time it was kind of just as a motivation. I spoke a bit about a Riemann surface structure for the torus, and it's mainly just so that somehow the definitions that we are going to introduce today don't come like just out of the blue somehow, because somehow what I noticed in the last lecture was that it is possible to somehow push down the Riemann surface structure of the complex plane to the torus, mainly because the natural map from the complex plane to the torus satisfies two properties, right? One is that it is a covering function or a covering map, this natural map from the complex plane to the torus, and second, that the transition functions are holomorphic. So and so the reason and the reason behind the natural map from the complex plane to the torus being a covering function is that such natural map is the projection, well, not only to a quotient by a subgroup, but actually to an orbit space where one interprets the subgroup by acting on the space through its operation, the operation that makes it a group, and that when one thinks in those terms, the corresponding action is properly discontinuous in the strong sense, right? So that's the reason behind the fact that this map is a covering map, and so we are going to be looking for actions that are properly discontinuous, but now, of course, in our context of actions on the hyperbolic plane, right? And then somehow later on, we are going to speak a little bit about the fact that one can induce Riemann surface structures, and that somehow this is going to be actually somehow the not so hard part, because the transition functions are going to be Mobius transformations, and we know that those are holomorphic. So somehow the really kind of hard property is to find is this proper discontinuity, and so somehow that's the kind of actions that we are going to be looking for, and somehow as a preparation, I'm going to discuss some proper maps and some like general properties of discrete subsets of the upper half plane. Yeah. Okay. So proper maps. So recall that in general, a continuous map between two topological spaces is called a proper map or proper function if the inverse image of any compact subset is compact in the domain. Yeah. So we're going to see that these certain evaluation functions are proper. So somehow that's the first objective. And by evaluation function, what I mean is that I pick a point in the hyperbolic plane. So in this case, in the upper half plane, and then I fix it, and then I'm going to evaluate matrices there. But somehow, of course, the way I can evaluate a matrix there is by really evaluating the associated Mobius transformation in the point. Right? So this evaluation map, what it does is it takes a matrix A and it sends it to the result of evaluating that matrix, or more properly, its associated Mobius transformation at the point. Right? And the lemma is that this assignment is continuous, and the proof is actually, I would say, more or less routine. So it goes along this way. So let's write our point z0 as its real plus I times imaginary part, and then one takes any element of the domain here, right? And then then this evaluation is this Mobius transformation evaluated at z0, and then one can just keep going and develop, right? But then in the end, the point is that you see here I wrote in blue or in cyan what really is a variable in the domain, right? So these are really like real variables, right? And then on this subset of R2 times 2, which one can think of being as just R to the fourth, on this subset, the assignment rule of this function is, you see, the real part is this rational expression in these real variables, right? Which, you see, z0 is fixed. So all these a0, b0 are constants. So this really is, you see, a polynomial of degree 2 in these real variables divided by certain polynomial of degree 2 in those same variables, and just the denominator never vanishes, right? And that's the real part, and the imaginary part sort of similarly, and actually even simpler, because this is just constant. This is the constant b0. And so my point is that both in the expression of this, both the real part and the imaginary part are just rational expressions in these four variables whose denominator never vanishes, right? So of course that by just basic calculus of several variables, that tells me that this is continuous, right? It would be actually even like a differentiable. So okay, so this is indeed continuous. Right, and now the first thing is what I said, that this map is proper. That is, that the inverse image of a compact subset is compact. So given a compact subset of the codomain of the evaluation, its inverse image, which of course consists of all those matrices which are mapped into K by my function, so it's all those matrices that somehow transport Z0 through K, or whose associated Mobius transformation transports Z0 into K. Well, that preimage is compact, so that's the theorem. And the way I'm going to prove it is by showing that this inverse image is both closed and bounded in R2 times 2, right, which is R to the fourth, as we said. And then because the compact subsets of Rn are precisely those that are closed and bounded, then it will follow. So K is compact in U, and U is an open subset of C, or if you want of R2. So this one is closed, and we know that the evaluation the evaluation map, this FZ0, is continuous. So the inverse image is closed. So that part is easy, and now we're going to see that it is bounded as well. And for that, what I'm going to do is I'm going to see that any element here, you see, when I write any element here in term when I write the corresponding matrix, I'm going to see the entry by entry that they are bounded. So by the way, here it should. Okay, so that's what I'm going to do. So now, since K is compact here, you see, if I draw U, let's say that this is the x-axis. So K is compact here, right? Oops. Well, okay. So that's not so perfect. Oh, okay. So let's see. Yeah. So K is compact there. So in particular, it's above certain horizontal line, which is strictly above the x-axis. So so there's this constant with that property, right? Yeah, for K, and also the norm is bounded here, right? So so there exists these two constant m1 and m2, so that K is above the horizontal line at m2, and the whole of K is contained in just the Euclidean disk with center at the origin and this radius. So so that means that whenever I take anything in its pre-image, when I apply the function, of course I land in K, so the evaluation satisfies these two inequalities. And this is just by compactness of K, right? Okay. And so this, of course, translates into this inequality. And we had already computed this imaginary part. Actually, it's here, right? So, well, of course, here it's a y naught instead of b naught. So this is just it's just a rewriting of these two inequalities explicitly in terms of the matrix A, of the entries of the matrix A. And then we start solving, because you see here what I'm going to do is I'm going to bound gamma. So I'm going to consider something in which gamma is easy to solve for, and then I introduce certain somehow like certain noise, right? But somehow certain noise that makes this expression become this norm. Right? So this norm, because this one, you see, from this inequality, I can move this to the left and this to the right, and so I obtain that this is strictly less than this quotient. And the point is that here I already have, here everything is constant, and here gamma is easy to solve. So to solve for, so I solve for gamma, and what I obtain is that gamma is really bounded by this constant. Okay, but somehow, yeah, it's not so hard. It's just the point is, in something where gamma is easy to solve, I introduce certain noise that makes it become some norm, right? And some norm kind of involved in these inequalities. That's really the main point. And similarly, when I go now into bounding alpha, it's similar. You see, a place where I can easily solve for alpha. Therein, I introduce certain noise, right? And then I'm really doing the same thing as I did here, but of course without the square. And once I'm here, then I use this other inequality, moving this to the right, and of course this one is bounded by. So again, I move this to the left, this to the right, so it's bounded by this one. And what I obtain is then I can solve for alpha, right? I can move this to the right, and then I see that alpha is bounded completely by certain constants. So by this times 1 divided by the norm of y naught. Okay. And then, yeah, so let me see. Yeah. And so then I'm going to quickly say how to bound beta and delta, because it really follows the same idea. You see, here I used these two inequalities to bound alpha and gamma, and the point is that I could do that because somehow here the appearance of gamma is always with z naught, and the appearance with alpha is always with z naught. And that allowed me to introduce some, like, the noise from which I could solve for gamma, and the noise from which I could solve for alpha. So somehow to bound delta and beta, now I want them to be accompanied by something related to z naught, so that I can play the same game. But of course here these beta and delta are not accompanied by z naught. So what I do is I just multiply by z naught inverse, and then I obtain this. And then from the inequalities I already have, I obtain this inequality and this inequality. And now using them and just the same technique, I can bound beta and delta. Yeah, okay, and then when I conclude that all entries are bounded, so this one is closed and bounded, so it's compact. Okay, and now, now really, I just want to kind of to draw a picture of in one situation. Yeah, so here this is an exercise which is just here we showed that the evaluation map from SL2R to U is continuous, and now the exercise just asks to show that now if we move on to PSL2R, the same is true, right? And kind of the same type of evaluation. Actually, there's some commutative diagram there. Right, and then one can see, you see, if we take in particular Z naught as our compact subset of U, of course, when one asks all those matrices with the property that the corresponding Mobius transformation maps Z naught to Z naught, what I have is the stabilizer of Z naught for the action of SL2R on U by Mobius transformations. And so you see, it's kind of, this is all those matrices that have whose Mobius transformation fixes Z naught. and it's all those matrices in SL2R that have this Z naught in U as fixed point. But being in U, this means that these elements here, all the elements here different from the identity, the corresponding Mobius transformations have to be elliptic. So if I see it here, then it's easy to see that this is really a circle in disguise, because it's you see, it's I have my so this is the real axis, and then I have my point Z naught, and when I consider here, it's the Mobius transformations in PSL2R that fix Z naught, so they have this as fixed point, and they have to be elliptic, so they are parameterized by the angle of rotation. Right? And then here one can easily see that this is really a circle. But here it's also a circle. And actually, if you think this map is 2 to 1, right? Because here two matrices here give me the same Mobius transformation, if and only if they differ by a minus sign. And this exercise asks to prove that here this stabilizer is also homeomorphic to a circle, and then restricted to the stabilizer, the projection really corresponds to the self cover of the circle given by the square function, by z goes to z square. And then somehow what I want is, so we know that this stabilizer is then a circle, and then in the picture of SU11, which is homeomorphic to SL2R that we saw, right? Oops. Okay, so that would be SL2R or homeomorphic to SU11, actually diffeomorphic, right? So, but let me just, yeah. And then we saw that somehow here this the skin of this solid object is all those matrices whose Mobius transformation is parabolic, and that the interior of this of the solid consists precisely of those matrices that whose Mobius transformation is elliptic. And you see somehow here, well, here I have to go back here, and the point is that when I consider one point Z naught, and I ask for all those matrices that leave it fixed, right? Whose Mobius transformation fixes it. Somehow, what I obtain inside, you see, in the interior of that solid, is somehow one of these circles that are like here. But of course, I mean, here somehow the drawing is supposed to happen in the interior. Right. So this is kind of an exercise to think about this. So that's how the stabilizers look, and you see somehow this point and this point, they really go to the identity to the identity function of u bar, and somehow and somehow this quotient, it really identifies somehow antipodal points. So here you can also see this this twofold cover of the circle by itself. Right? I mean, you have to identify a point. You have to identify those points. And the way to identify is kind of just to take from this circle to itself by z goes to z square. Okay. Anyway, so that's somehow just so that you have some kind of some mental image of how these sets look like, because then when you let now z not vary, somehow this circle somehow then starts to vary around, right? So it somehow like starts. Oops. Oh, okay. So okay, kind of starts varying around, but inside, kind of in the interior of that figure. And then if z not lived in a compact set in U, somehow that compact set is kind of can be more or less located here as a cross section of where of this variation of circles. Anyway, that's just kind of to have some intuition. Yeah, some exercise which is more like a bit more advanced if you know some say algebraic topology, because then somehow this really starts looking like some sort of fiber bundle, right? I mean, it starts to look like a some fiber bundle of circles here. So somehow, if you know some algebraic topology already, some a bit more advanced algebraic topology, whether these are really fiber bundles or not, these evaluation maps. But okay, so this is just this was just kind of a topological preliminary, and it's what that these evaluation maps at points at any given arbitrary point of U is a proper map, right? So inverse image of compact is always compact. That's going to play a role. A bit more topological preparation, and it's about discrete sets. And so a subset of a topological space is discrete. Well, here's the definition. If every point in my subset has an open neighborhood with the property that, I mean, being an open neighborhood of S, of course, S belongs to A, but somehow it's the only point in A that belongs to S. So somehow it's somehow isolated. But this one has to be careful when one says isolated, because how to say, I mean, another way of saying this is that a subset is discrete if it doesn't accumulate in itself, right? So that doesn't accumulate in itself, so that every point in S has some neighborhood with the property that it's the only point there, right? But kind of that when one considers the punctured neighborhood, where one deletes S, no other point of S is in that punctured neighborhood. right? And that means not accumulating in S. But somehow the reason I say this is that, for instance, well, of course, Z is a discrete subset of R, so this is really kind of an obvious example. But the point is that you see this set, the set of all 1 over n's for positive n's, is also a discrete subset of R, despite the fact that it has some accumulation point in R. Right? So 0 is an accumulation point of this set, but the point is that 0 is not in the set. And when I consider only the points in the set, no one of them is an accumulation point of the set. Right? So this one has some accumulation point, but all the accumulation points are outside, and it doesn't accumulate in itself. So that's kind of a small subtlety. So discrete subsets are allowed to accumulate. It's just they are allowed to accumulate elsewhere, not in the set. And of course, then here, if I attach 0, then of course this one is not discrete, right? Because then this one accumulates in itself, right? In this point. So one has to be a bit wary when talking about discrete sets, because one usually thinks that, okay, something is discrete, so it doesn't accumulate. Right? But the point is that it doesn't accumulate in itself. That's what one always has to remember. And actually, in order for this to be an equivalence, somehow one needs to impose this extra condition that if you start with a closed set, then it is equivalent for it to be discrete and for it to not accumulate, not only in itself, but to not accumulate in the whole space. Right, and kind of similarly, if you start with something that doesn't accumulate in itself, then it's equivalent for it to be closed and to not accumulate in the whole space. Right? And and then the handing exercise, not accumulating in the whole space is equivalent to being closed and discrete. Right? I mean, somehow closed means accumulation points all belong to S, right? And discrete is, okay, no one in S is accumulation point. So then there you go. It's like at least this implies this, because kind of any accumulation point has to be in S because of closedness, but no one in S is accumulation point. So there are no accumulation points in X. So okay, so I pretty much did this. Okay, so just kind of just a warning. Discrete, just alone discrete, doesn't mean not accumulating in the big space. It only means not accumulating in itself. Now, fortunately for subgroups of Lie groups, one doesn't have to worry because it is equivalent not accumulating in the whole space to being discrete. Right. So okay. So this is not a course on Lie groups. So this lemma is true in general for Lie groups, but if you feel uneasy thinking about Lie groups, then just think that G is either SL2R, let's say, or SU11, which is just isomorphic as a Lie group to SL2R, or that it is PSL2R. Right. So, and so this lemma says as I said, for subgroups there, you don't need to worry about this remark. About the remark I just made about discrete sets. And it's equivalent not accumulating in the whole space is equivalent to not accumulating just at the identity. This is very useful. So one only needs to check that the identity is not an accumulation point of the subgroup in order to know that the subgroup doesn't accumulate anywhere. And this is equivalent to the seemingly weaker condition that gamma doesn't accumulate in itself, right? Weaker than the first one. Okay, so now for the proof, so here because if a subset doesn't accumulate anywhere, then one can say that it's closed and discrete. Then this one implies, it of course implies 2, but it implies 3 by the handing exercise. So I have 1 implies 3. So maybe let me mark it. Oops. So this is done. 1 implies 2 is obvious. 3 implies 2 is also obvious because of course the identity belongs to any subgroup. So if the subgroup doesn't accumulate in itself, in particular it doesn't accumulate in its own identity, which is the identity of the big group. So 3 implies 2 is also obvious. Yeah, so to close the chain, maybe then I need only 2 implies 1. So for that, well, assume that it does accumulate in G, and what I'm going to do is a sequence that accumulates in a sequence of elements of gamma that accumulates in G. I'm just going to manipulate it to produce a sequence of elements of gamma that accumulates actually at the identity, right? And you see, somehow the point is, if this one accumulates, let's say in G, somehow what comes to my mind is kind of to multiply by some inverses. So that's somehow what comes to my mind. But of course, if I just take if each gamma n I multiply it with the inverse of gamma n, then of course what I obtain is just gamma n inverse gamma n, which is just the identity, and so and then this sequence is just a constant sequence. So it's not a good sequence for accumulation, right? So somehow it comes to my mind to multiply with inverses, but just multiplying with the same inverse at each step, kind of with the inverse of the corresponding nth member, is not really the best idea. So somehow the next thing is kind of, okay, then gamma n multiplied with gamma n plus 1 inverse, and then see if that works, right? Because for accumulation purposes, one can just take the sequence to be of pairwise distinct elements, and then if one considers that element, of course that element is not the identity because gamma n and gamma n plus 1 are different. So this one is not the identity. So this one, none of them is the identity. And when you take the limit, you see you use this, that the limit of the product of two converging sequences is the product of the limits. And the product of the limits, well, this one converges to G, and this one converges to G inverse. And so this limit is the identity. Right? I mean, of course, here, kind of, if you think for a general Lie group, then of course there are some things that I have to justify, right? So what does it mean to converge in an arbitrary Lie group? And I would really have to prove this. Oops, sorry. to prove that the limit of this limit for converging sequences Gn Hn, this limit is the product of the limits, and that the limit of the inverses is the inverse of the limit. I would need to really justify that. But if you think of G, just as this SL2R, let's say, then in that situation I don't really need to worry, because the operation that makes SL2R a group is just given by polynomial rules. Right? So one can really check this exercise directly in SL2R.
Could you multiply by G inverse instead of taking?
Here, I mean, the problem is that you don't know that G is in gamma. I mean, yeah. So you want to show that we're assuming that gamma accumulates in G, and now I want to see that gamma accumulates at the identity, right? But the problem is that this one may fail to be in gamma. Yeah, but otherwise it would work. Yes. And on the other hand, this sequence is kind of it clearly consists of elements of gamma. Okay. Okay, and then this finishes the chain, right, of equivalences. Right, and then as a corollary, every time I have a discrete subgroup of G, that discrete subgroup automatically, by the lemma, doesn't accumulate in the whole space, and so by the exercise, it's also closed. Right? It's closed and discrete. Okay, so discrete subgroups of Lie groups are always closed. Or if you want, discrete subgroups of just SL2R or PSL2R are always closed. So, at least for subgroups of SL2R and PSL2R, whenever we say that discrete subgroup, we automatically know it doesn't accumulate in the whole space, not only in itself. Yeah, another exercise, which later on is going to be important, that if I have a closed discrete subset of a space, then its intersection with any compact subset is always finite. Okay, it's actually not so hard. Okay, and then we have our preparations, which were if I take any given point in Z0, the evaluation map given by evaluating at that point is a proper map. That is inverse image of compact is compact. And we have an equivalence, which is that for a subgroup of SL2R or PSL2R, it is equivalent for it to be discrete and to not accumulate in the whole space, and also to not accumulate in the identity. So somehow to check that something doesn't accumulate in the whole G, somehow I can just check that it doesn't accumulate at the identity, and this is very very useful in kind of in practical terms. Yeah, and then we arrive at somehow to the beginning of our study of the property that produces covering maps from U to orbit spaces, U modulo orbit space by the action of subgroups of PSL2R or subgroups of SL2R. So definition, I mean, kind of just reminder that if I have a topological space and a group that acts on that topological space by homeomorphisms, and by that I mean is that for each element acts on Y by a homeomorphism. So the corresponding, the action by gamma, by the corresponding lowercase gamma, is a homeomorphism of the space. So whenever I have an action by homeomorphisms, I say that the action is properly discontinuous in the strong sense if every point has an open neighborhood, Vy, with the property that every element of gamma different from the identity, moves Vy sufficiently far away. In other words, the only element of gamma that doesn't move Vy very far away, that has the property that after moving I still intersect Vy non-vacuously, so I'm not landing very far. The only element that does that is the identity, right? So all non-identity elements move Vy sufficiently far away. Okay, so that's proper discontinuity in the strong sense, and somehow, unfortunately, somehow we are going to see that we are going to be forced to also consider a weaker version of this notion, which is proper discontinuity in the weak sense. And proper discontinuity in the weak sense is the following relaxation of this condition: that there be an open neighborhood of my arbitrary point with the property that the set of elements of gamma that don't move Vy sufficiently far away, so that this intersection is not empty, is finite, right? So of course, a properly discontinuous action in the strong sense is also a properly discontinuous action in the weak sense. But we are going to see that there are some in the weak sense that are not in the strong sense, and we're going to see that somehow the reason is that gamma may have elliptics. So okay, but that's going to be in the future. So the first equivalence is that one can think in both ways, that I want to characterize properly discontinuous actions, either in the strong or weak sense, in terms of some intrinsic topological properties of my subgroups of SL2R, or we can think also that I can characterize discrete subgroups of SL2R, or I want to characterize discreteness in terms of the topological property of the corresponding action of the subgroup of SL2R on U by Mobius transformations. We can think like both ways. In terms of in terms of the desire of producing covering maps from U to orbit spaces, somehow it seems that really what we want to characterize is when this is a covering map or when the action is properly discontinuous in terms of the topology of the subgroup. But anyway, so the point is that here, unfortunately, if one just takes discreteness, the corresponding topological property of the action is not discontinuity in the strong sense, but in the weak sense. So somehow this theorem really is the reason why we have to relax our the condition. But okay, and the characterization then is as follows. My subgroup of SL2R is discrete if and only if, and this is already a property of the action on U by Mobius transformations, which is orbits are closed and discrete, and stabilizers are all finite. So any given orbit doesn't accumulate at all in U, right? Closed and discrete, and stabilizers are finite. And the third condition is proper discontinuity of the action of gamma on U in the weak sense. So it's going to be a bit heavy, and there's going to be axiom of choice anyway. So take so let's say 1 implies 2. So take a point and a compact set. So I know that the pre-image of my compact set under the evaluation map is compact in SL2R. And so I have my compact set, my compact subset of SL2R, and my closed discrete subset of SL2R. And so this intersection is finite by one of the previous exercises, by this exercise. So this intersection is finite. And so you see the gammas that take Z naught into K form a finite set. So in particular, those images of Z naught that lie in K also form a finite set, right? I mean, the number of elements here is actually less or equal than the number of elements here. Okay, but then that means that the intersection of the orbit with any given compact subset of U is finite, and so this one is a closed discrete subset of U, again by this I'm using the converse actually, I think. I'm using the converse, right? So that I know that this intersection is always finite, and then I'm concluding that this is a closed discrete subset of U. So this is really the converse. So let me see. Yeah. Okay. So somehow I'm already saying that it is indeed true. But okay. Okay. So orbits are closed and discrete. And now I only have to show that stabilizers are always finite. But then again, the point is that we already saw how to compute the stabilizer in terms of the evaluation. Right? The stabilizer is just all the matrices that send Z naught to itself. Right? So this is the stabilizer, and Z naught, of course, Z naught is compact because it's only one point. So this one is compact, and so its intersection with this closed discrete subset of SL2R is finite. But if you think about it, sorry, here it's the stabilizer in SL2R, sorry, and the stabilizer in gamma is the set is those in gamma those in gamma that are also in the stabilizer according to SL2R, and this is finite. Right? This is finite. So the stabilizer in gamma is finite. Right? Of course, the stabilizer, as we said, the stabilizer in SL2R. This one is homomorphic to a circle. So this one is of course not finite, but this one is finite. Okay, and then that finishes the proof of 1 implies 2. Yeah, and then I'm going to prove 2 implies 1. So let me right, 2 implies 1. Right? So I'm going to assume that this is not the case, that gamma is not discrete. And because of the previous characterization, what I know is that gamma then accumulates at the identity. Yeah, and so since the identity is an accumulation point, it is a limit of elements in gamma, an honest limit, right, of something not non-stationary. So there is a sequence of pairwise distinct elements of gamma that tend to it, that converge to it. And so you see, when I evaluate at Z naught is then the limit of these evaluations, right? And for that I can just write. I mean, for that I can just write the correspondence rule of this one, and then see that, how to say it. Reduce this to a property of limits in Rn. Right? So okay, and once I know this, you see, the point is that here I'm seeing Z naught as a limit in its own orbit, right? So I'm assuming that this is not the case, and I want to prove that this is not the case, right? So I want to prove that either the orbit is not closed discrete, or the stabilizer is infinite. Right? Now, if this one is discrete, so if this one doesn't accumulate, let's say just in itself, then you see, here I'm writing Z naught as a limit of elements in this orbit, but then Z naught would not be an accumulation point. So that forces this sequence to be stationary. That is, that after some point, everything is just equal to the limit, to the limit. But then what I have is all of these are pairwise distinct elements of gamma that fix Z naught. So the stabilizer is infinite. And then I got what I wanted, right? That if gamma is not discrete, then either this one is not closed discrete, or the stabilizer is infinite. Okay, now for 2 implies 3. Yeah, so I want to show proper discontinuity in the weak sense, and I'm going to assume, that orbits are closed discrete and stabilizers are finite. Yeah. So I take a point, right, and then somehow I'm going to assume that that proper discontinuity, which is what I want to prove, somehow fails at this point, so that actually for every, no, it doesn't matter which open set you give me excuse me, it doesn't matter which open set you give me around around the point. The set of gammas that don't move it sufficiently far away is actually infinite, right? And this, it doesn't matter if you take a very small, how small you take your open set V. Okay, and what I'm going to do is I'm going to construct a sequence. I'm going to come back to this axiom of choice, to the use of the axiom of choice a bit later. But so the point is that I'm going to use this, that this is for every open set, to then consider the case of all open disks of radius 1 over n around W naught, to produce certain sequence. And so when I consider the open disk around W naught of radius 1, and here this H is just so that it's an open disk of radius 1, but in the hyperbolic sense, right? So so that's what this H means. So it's not Euclidean radius 1, it's hyperbolic radius 1 with this hyperbolic center. Yeah, and then for this open set, for this open disk around W naught, I know that I can find that there are infinitely many here, for this choice of V. Okay, so I just pick one, and then for each n, what I do is, you see, at the nth step, somehow I assume that I already constructed n distinct elements of gamma, and then I'm going to move on to the next step. And then here's first of all I'm going to take an element different from the ones that I already constructed in the first n steps. And then I'm going to consider, I consider as my open set here, the open disk with hyperbolic center W naught, but now with this center, sorry, with this radius, 1 over n plus 1. Right? For this choice of V, this set is infinite, right? So of course I can find a gamma, and this here is gamma n plus 1. with this property, but also since this set is infinite, I can also choose, I of course can choose it so that it's indeed different from the previous ones. Okay, once I did that, then I noticed the following. The distance from W naught to gamma n of W naught is at most 2 divided by n, right? And this is by the triangle inequality, because what I do is I take one point in this intersection. So let's say W in B H W naught 1 over n intersect gamma n of that thing 1 over n, right? And then the distance from W naught to gamma n of W naught is less or equal than the distance from W naught to W plus the distance from W to this one, and then I play around. You see, I apply gamma n inverse, and then I arrive that each of these two summands is less than 1 over n. So this gives me less than the 2 over n. And so what I obtain is that, again here, that this sequence, the sequence gamma n of W naught, converges to W naught. And again, so what happens that yeah, here I should have here it's we cannot have this one closed discrete, and the stabilizer finite at the same time, right? Because if this one is closed discrete, then from this equality, what I obtain is that then this sequence is stationary, and if it's stationary, what I see is that all those gammas fix W naught, but those gammas by construction were all different. So I cannot have at the same time closeness and discreteness of orbits and finiteness of stabilizers. And what this shows is, kind of just coming back, is that from assuming that the action is not properly discontinuous in the weak sense, what I show is that I cannot have both of these properties simultaneously. So that proves 2 implies 3. And then here, just some discussion, I mean, some about the axiom of choice, right? I mean, the point is that of course, when I consider you see this radius 1, of course I can pick one with this property, and for n plus 1 I can pick one with that property. But the point is that, since in order to actually be able to form the whole sequence, I need to be able to make all these choices at the same time, and not just here once, and not just here once for my given n plus 1, but I want to be able to do it fully simultaneously for all values of n. And well, I mean, of course, again, this is not a course on set theory, but in order to do that simultaneously, I need the axiom of choice. But okay. And finally, is it finally? Yeah, so I'm going to show 3 implies 2. Okay, so take a point. I want to show that its orbit is closed discrete and its stabilizer is finite. And what I know is that there is some open neighborhood of the point with the property, and I just say it once more, with the property that the number of gammas that don't move it very far away, that is with the so it's not very far away because it moves, but this image still overlaps V, so it's not very far away. Well, the number of such gammas is finite, and there is something which is easy from this, because anything that fixes Z naught, you see, fixes Z naught. So in particular for this set, for this open neighborhood, Z naught is not mapped far away by anything that fixes it. So this one is actually a subset of this set, so it's finite. So that was an easy consequence, and not so straightforward. It's going to be that this one is closed discrete. So suppose it's not discrete. So here is suppose that it accumulates in itself, right? So suppose that this point, which is of course in the set, is an accumulation point of the same set. Okay, so what can we do then? Then this point can be approximated in a non-trivial way, right? Kind of in a non-stationary way. That means that for each integer there is someone, and here it should be capital gamma. There is someone in gamma with the property that, well, these are different because I want to approximate the point, but in a non-stationary fashion, right? And this point is sufficiently close to the point I'm approximating, right? So by less than 1/n. Okay, and then from here, if I apply gamma inverse, here I obtain Z naught. Here I obtain gamma inverse of gamma of Z naught. Since these are different, and gamma is an a hyperbolic isometry. So the disk with this center and this radius goes to the disk with center gamma inverse of this, so Z naught, with the same radius because it's isometry. And so what do I obtain? What I obtain is that this point is here, so here, but of course also Z naught itself is in this disk, right? It's the center of the disk. So when I apply gamma inverse gamma n to it, that one is in the image of this disk under the transformation. So this one is in the image of that disk under the transformation. So somehow this this is actually the easy part, and this, and here I have this other part. Okay. So you see, I'm starting to move towards contradicting proper discontinuity. So now this is at the nth step, okay? And now I want to see what happens when I move forward. Right? But when I move forward, of course, this, you see, if I keep the center, but I decrease the radius, then of course I shrink. So I really have this inclusion. And if I write that, then it's clearly true, right? Yes. Because this one is contained in this one, right, and then I just apply this thing. Yes. So if I write that, then this is obvious, right? Okay. Right, and then you see this point really lives in this intersection, because I mean this point lives here, I mean by the same property here. I mean, because this was for every n, so if I move forward, then I still have the same property, right? But then now I know that this point lives in this intersection, and now I know that this element really has the property that when I put it in place instead of G, it really gives me not empty, right? Because I have this common point of the intersection, and now it's correct. And all of these are, this is infinite because right, this is infinite because all these points are different, and if all these points are different,
because the sequence is not,
it's not stationary. Yeah. So see, yeah. So these points are eventually all pairwise different. Or I mean, I should be more careful, right? Not only that, I mean, because they yeah, no.
Because it's not discrete, there has to exist a sequence.
Right.
Is not stationary.
Yeah. It has to contain a sequence,
right,
which really doesn't repeat elements, right, at all, right? And then once you know that, then the gammas themselves can have to be all pairwise different, right, because otherwise these points would be this. Yes. Okay, and then you know that this is infinite. Okay. Yeah, and then what happened? That if this is not discrete, if this is not discrete, then it doesn't. Then for any size of disk around Z0, this set is infinite. So at least for open disks, the condition of weak proper discontinuity fails. But if it fails for open disks, it fails for all open sets. Okay. Now, and it was, okay, and this was just for such a silly mistake. Okay. Sorry about that. Okay, and then this finishes the proof of the theorem. Right? I mean, of course, one of the questions then is, okay, but then you see, if what you really wanted was proper discontinuity in the strong sense, because that is the one you know that leads to covering maps, then what extra restrictions do you need to impose in your group, right? And then we're going to see that the condition is that gamma be torsion free, or equivalently that it doesn't have any elliptic Mobius transformations. But so at least that question can be solved. Like, how do you really obtain what you wanted? This I think is going to be in the next lecture, if I'm not mistaken. Yeah, a couple of exercises. You see, you see, I can of course project from SL2R to PSL2R. And then the first exercise is that if you take a subgroup of SL2R, it's equivalent for it to be a discrete subgroup here than for that's equivalent to its projection being discrete here, right? And then the next exercise is the converse. If you now take a subgroup here, it is equivalent for it to be discrete to its pre-image being discrete in SL2R. So somehow the projection is well behaved with respect to discreteness here and discreteness here. So that's what these exercises ask for. And then we get to the definition of what is a Fuchsian group. So a Fuchsian group is any discrete subgroup of PSL2R. And then here you can see that it's kind of being a discrete having a discrete subgroup of PSL2R is pretty much equivalent to having a discrete subgroup of SL2R. Yeah, so let me just finish, like maybe 1 or 2 minutes. Right, I mean, some kind of obvious example, right? I mean, this SL2Z is obviously discrete, right? I mean, it's their entries, they really cannot accumulate, right? I mean, because convergence in R4 is equivalent to convergence entry, coordinate by coordinate, right? So this one is discrete, so this is kind of the prototypical example of a Fuchsian group. Finite subgroups are of course Fuchsian. They are of course discrete. And so the question is, okay, so now you know that really the subgroups that somehow have the hope of having nice topological properties or consequences for the projection from the upper half plane to the orbit space U modulo gamma are the Fuchsian groups, right? So those are the ones that for which you have the hope of having some sort of covering map. And then the one of the questions is, okay, how about criteria, right? You see, like typically what happens is that one is handed a bunch of Mobius transformations in PSL2R, and then one is asked, is the subgroup they generate Fuchsian or discrete, and how do you decide it, right? Or do you have a method to constructing a discrete subgroup of PSL2R or equivalently of SL2R? Unfortunately, there is an answer, and it's Poincaré's polygon theorem, which is going to say that if you start with certain hyperbolic polygon and certain set of Mobius transformations that pair the sides of that polygon, and if these Mobius transformations satisfy certain like global properties, which are actually not so hard to check whether they are satisfied or not, then the subgroup of PSL2R these Mobius transformations generate is discrete, and somehow the polygon you started with has certain geometric relation to that subgroup, namely it's a fundamental domain. So somehow, fortunately, there are ways of producing Fuchsian groups. And as I said, there's also an answer for the question, how about the groups that really give you, that actually give you actions that are properly discontinuous in the strong sense? And the answer is going to be those subgroups that don't have elliptic elements. So at least somehow what's nice is that at least for the difficulties we face, there are answers. Yeah? And okay, and then I ran out of time.